and I'm going to announce the material which will be covered by the final at the end of the lecture today. Actually, we are almost finished with the material which I have to teach, so maybe next week on Monday I will finish it. Then afterwards I will move on to chapter 16, which is very important for engineers, vector calculus, and I will introduce some. I don't think I can cover the whole chapter, but I will at least cover a couple of sections. But more or less, this depends on you, because if nobody's coming, then I'm not going to spend time teaching these details. Then in 2 weeks we have the final, and after the final, I think we have still 2 or 3 times left, and maybe we can spend 1 or 2 times discussing examples from previous Hoikaus. In particular, I can teach you some tricks how to score high in the Hoikau without doing too much computations. Okay, so last time we have discussed, the last thing we have discussed are triple integrals. Now I remember the last example I showed you was this one. So dz dx, and I asked you to change the order of integration. So you have here a iterated integral, and you were asked to change the order of integration to first. So first you first project the solid over which you integrate onto the xz plane. You were asked to find the integration where we first go over the zy plane, or for instance in this direction, and then dx. You remember I showed you this example last time. Does anyone has a solution? I hope you thought a little bit about this example, because such examples seem to be quite easy, but in fact they are not that easy. Okay, so because sometimes in the Hoikau you have such an example where you have given here some of the limits, okay, and the other one you have to fill in. This is one way to choose such an example for the Hoikau. Another way is multiple choice. So I give you 4 choices, and you have to pick out the right one. You have to decide which one gives the same value. Now I explained already last time how to do this. So the first thing you certainly want to do is you want to plot the solid over which you integrate. So here, okay, so the x is from 0 to 1, the z is from 0 to 1 minus x squared, and the y is from 0 to 1 minus x. Okay, so how does this solid look like? Okay, so here you have x, here you have y, here you have z. Of course, we just have to look at the boundary. Okay, so here the boundary is given by z is equal to 1 minus x squared, the cylinder. Okay, so this is in the zx plane. Okay, so you have something like so here you have 1, and you have this cylinder. Okay, so you have here this cylinder where the y-axis. So you have here, this is a parabolic cylinder. Okay, so this part here. We will see that because x, y, and z are all larger or equal than 0, so we are in the first octant. We do not have to care about the part of the surface which is of the solid which is not in the first octant. Then from here we see that y is equal to 1 minus x. Okay, so this will give you a plane, this plane here, where you have here 1 as well. Okay, so you have this plane here and this cylinder. So in order to plot this, it's not so complicated here. So this will look like this here. Okay. So this is the solid over which you integrate. Now you see that for this way of integrating over the solid, okay, we have to project first the solid onto the xz plane. Okay, this is easy, okay, because you see that if you project it on the xz plane, the projection you see already here, okay, is given by it's just given by this curve here. Now, if you project the solid onto the xy plane, it's also not complicated. What you have is a triangle. Okay. Also, the projection of the solid onto the yz plane is not complicated. Okay, because it's just this rectangle here. So, if we have to set up this integral here, we have to project first onto the yz plane. We see already here the projection. So the projection is given by this unit square. Now, the only thing which is complicated to figure out is, okay, so you are first going to integrate over the unit square. So y from 0 to 1, z from 0 to 1. But the range for x, okay, will depend. You see that if you're at a point here, you have to go from 0 to this surface here. Okay, but if you are here, you have to go from 0 to the plane. Okay, so the range of x will depend on where you are in the unit circle. Okay, so you have to first figure out, okay, the projection. You have to project this line also back to the yz plane. But this is not complicated because you just look at these two equations here. Okay, so you see that from those two equations you have z is equal to 1 minus, and you replace here x by 1 minus y. Okay, which is 2y minus y square. Okay, so this is what you get. This is the function if you project this line onto the yz plane. Okay, so you have we can check this easily here. So if you plug in y is equal to 0, you are here. If you plug in y is equal to 1, you are here. Okay, this will give you some curve. So actually, it's not possible to rewrite the integral, okay, into this form by just using one integral. You have to split it into two parts because the range for x will be different whether you are here or here. Okay, so this will become. Okay, so we always go first over y from 0 to 1. Then over z from 0 to this curve here, 2y minus y square. So this means we pick a point here, and then the z goes from 0 to the x. Sorry, goes from 0 to this plane here. So 1 minus y. Okay, f of x, y, z. And then you have dx, dz, dy, plus, but this is just one part. The other part is, you have to choose a point here. So this means the integral goes from 0 to 1. The second integral goes now from 2y minus y square up to 1. So this means we integrate along this line, such a line here. And for the x, you have now to choose the other one, this one. Okay, so the x goes from 0 up to, you see, to the cylinder. Okay, so a square root of 1 minus z. And then f x, y, z, dx, dz, dy. So this would be the answer. So sometimes in a Hoikau we have examples like this. For instance, you have 4 choices, and if you maybe one of the choices is this one of the choices is this one, and then 2 others, and the answer is none of them is the correct one. So you have to be careful here. So you see sometimes this kind of, you have given iterated integral, you change the order of integration. It's not so easy, okay, because it's also not so complicated. But the first thing you should do is you should plot the solid, okay, and then the only thing you have to try to figure out is so for this example, because you go first over the YZ plane, so you have to project the solid onto the YZ plane, and then you have to determine the range for x. Okay. Last time we saw an example where the projection is not completely obvious how to project onto the coordinate plane. Okay. This time we have an example where the projection is easy because you see it's a square here, but to determine the right range for x, okay, you still makes necessary that you have to think a little bit more, because you also have to project this line onto the xz plane. Okay, but making a picture is the way to solve something like this. After you have the picture, everything is getting easy. Okay, so any questions? Now, since I haven't yet discussed any applications of the trivial integral, we should do this. I stressed this already last time. So this is the difference compared to the double integral. When we introduced the double integral, we had a problem which we wanted to solve. Namely, we wanted to compute volumes of certain solids. And from this question, we were naturally led to the definition of the double integral. The trivial integral was different, because for the trivial integral we didn't give any motivation. We just used the same way of we just extended the definition of the double integral to a trivial integral. So we still have to find some motivation for considering this object. Of course, one motivation would be you compute hypervolumes in the four-dimensional space if you accept this as a motivation. Other motivations are, okay, you can use it to compute volumes. This, of course, is quite easy. So if you have to compute the volume of a solid, okay, you can do this by a trivial integral, and then the function equal to 1. Okay, so like this you can compute volumes. Of course, if you would take into account the measure at the units, okay, the unit would be the wrong unit, but the number is the same. Okay, so for instance, if E is of type 1, we defined this last time, so this means, okay, you can write this formula as a double integral over some d, and then you go from some function u1 xy to u2 xy d set, and then you have a dA. Then you see, okay, what you get is this is the double integral over d, and then you have here u2 xy minus u1 xy dA. A formula which is pretty clear. So here, what you compute here for the first one is you use the double integral to compute the volume below this function and above the xy plane, and here you use the double integral to compute the volume below this function, below the function u1 and the xy plane, and you subtract those two in order to get the volume of the solid E. Okay, so let's maybe just look at an easy example, just to have some more examples where we use trivial integrals. So use a trivial integral to compute a solid. Bounded by x squared plus y squared is equal to 9. Then y plus z is equal to 5. And z is equal to 1. Okay, so first, the first thing is always try to plot it. It's not so easy to plot it, but at least try to understand how it looks like. So you see that as z is equal to 1, okay, is this plane here. And then we have here another plane given by this equation here. So this plane is y plus z is equal to 5, so you have something like this here. Okay, where this point here, this point is 4. And then you have here this, I'm not really able to plot this. So this is the most important thing for me, okay? Because you see this, this will give you some part which is sandwiched in between those two planes. And then you have the cylinder x squared plus y squared is equal to 3. And you see that because the radius is equal to is smaller than 4, okay? So these two planes, okay, will cut out a piece of this cylinder. But you see that from this, you see already that the projection onto the xy plane is just a circle with radius 3. Of course, for this you have to make sure that the intersection of the two planes is larger than that. This point is larger than 3. So you have here the circle with radius 3. So what you have to do is you have to go over the circle, and then you have to go from this plane up to this plane here. Okay, so the triple integral over the solid is equal to, so first the double integral over this circle, so x squared plus y squared smaller equal than 9. And then in z direction, you just go from 1 to 5 minus y, then dz, and then dA. Okay, so you see that this will give you and here what you have is 4 minus y dA. And for this, in order to, the reason why I chose this example is, in order to solve this, you need nothing. You don't have to write out the boundary for this integral here. Because this is one of the examples in our textbook. I also checked the solution manual. The author is really computing this. Okay, it's not necessary. Because you see that if you look at the second function y, okay, we saw today in the in-class homework, okay, this is an odd function. And today in the in-class homework, we had a rectangle, but also this domain is symmetric about the x-axis. So the second one will be equal to 0. And the first one is 4 times the area of the disk. Okay, so you have 36 times pi. Okay. This is one of the examples in our textbook. If you choose if you look at the solution manual, you will see the author is really computing this. Not necessary. It's much quicker. So if you have to solve such examples, okay, for the Heuker also, try to keep things as simple as possible. Okay, so this is one application of triple integrals, computing volumes. Other applications which you find in our textbook are from physics and from probability theory. Now, one other application you certainly know this from physics. So if you have a solid which occupies some space region E, and you know the density of the solids, so if this describes the density of the solid of the space region E, it's not very precise, of the mass which occupies the space region E, then we know that you can compute the mass as triple integral over E, and this is the definition of the density. Okay, so you just sum over the density. Okay, so this will give you the mass of the solid object which occupies the region E. And we also know normally what is defined in physics are the moments about the coordinate planes. So for instance, we define the moment about the coordinate plane, the xy plane. So the definition of this is Okay, you just look for every point in E. You look at the distance of this point to the xy plane, which is just z, and then you multiply with the density. And you do the same for the other coordinate planes. So you have a mx z, which is the triple integral over E y rho x y z dv, and you also have a m y z, which is the triple integral over E, and then you have a x rho of x y z dv. Okay, this is the so-called moments about the coordinate planes. And the reason why they are important is because you can use them in order to compute the center of mass. Okay, the center of mass. So if you know them, then the center of mass is given by the point where you have here mx. This should be yz over m. Is the distance to the this should be xz over m, and this is which one is missing? Xy over m. Okay, so this helps you to compute the center of mass. Okay, so this is another application. I don't want to do an example. Except of those moments about the coordinate planes, you can also define the moments of inertia, which are now about the coordinate axis. So for instance, the moment of inertia about the, for instance, x-axis, you take for every point, you take the distance squared to the x-axis and multiply it with the density. And you might know from physics, the moment of inertia are important in physics. Okay, so this is one application. The other application which you find in our textbook is, which is pretty similar. So this kind of concept you see here is frequently used in physics. So normally, for instance, if you have a charge which occupies some space region E, okay, then normally you describe the charge by the charge density. And you compute the charge, again, by triple integral, which means summing up over all the charge densities. So you have this very often in physics, that you have some quantity described by some density, and you kind of sum over all points in the space region in order to get the quantity you wanna compute. This is a principle which is not only used in physics, which is also used in mathematics, namely in probability theory, where we do the following. So in probability theory, we study random events. So you have a random experiment, an experiment whose outcome is random. So for instance, you have a random vector. So a random vector. Every coordinate is called a random variable. Now, what we are mainly interested in probability theory is computing probabilities. So the probability that the random vector lies in some space region. Okay, so we are normally interested in computing something like the probability that x, y, z lies in some E. Okay, and the way we describe random vectors is we give densities. So it's just the same principle you just saw for masses. Okay, so the way we describe masses is we give the density. Okay, also here we give the density of the random variable. And we use, so the density of the random variable kind of tells you in some point, okay, how much probability is concentrated in this point. So you have a function of 3 variables, okay, which will describe you these probabilities, and you use this function in order to compute the probabilities. And this function in probability theory we call density function. So normally we use a density function in order to describe such a random vector. And using triple integrals, we can then compute certain probabilities. Okay, of course there are certain properties which such a density function has to satisfy. One of them is larger or equal than 0. And the other one, which follows already from this property here, is if you choose for E the whole space, then because the random vector has to lie somewhere, okay, so the probability should be equal to 1. Okay, so this function normally has to satisfy this property that if you compute this integral, should be equal to 1. Okay, so let's look at an example. Now these are the objects which are studied in probability theory, and you should see here, because I just showed you before the situation for masses. You should see this more or less the same. That's why normally we consider this function in probability theory. We say that this gives you the probability mass concentrated at the point xy of z, xyz. The reason for this is because the situation for masses is pretty similar. Okay, so for instance, the following example. So assume that our random density, our density function is given as follows: c times x times y times z with x between 0 and 2, y between 0 and 2, and z between 0 and 2, and 0 otherwise. So this means that our random vector will be inside this cube here with probability 1. We can choose the c such that the probability, if we integrate over this cube, then the probability, the density function, the integral over the density function must be equal to 1. That's how we can determine the c. Okay, so the integral from 0 to 2, the integral from 0 to 2, the integral from 0 to 2 over the density function, which is c times x times y times z, and then, for instance, dz, dy, dx. The order is not important because we see that this function can be written as a product of a function which just depends on x, a function which just depends on y, and a function which just depends on z, and this will make the iterated integral split into the product of 3 integrals. Okay, so you have c times now computing the x squared half evaluated at 0, 2, okay, which is 8, so 8c, and this must be equal to 1. Okay, so c is equal to 1 over 8. Okay, so you see that the density function of this probability distribution, the density function, forget about probability distributions, this you will learn in probability theory. This density function, okay, since if you integrate over the solid, it must be equal to 1, we can easily determine the c. And now we can use this in order to compute certain probabilities. in which we might be interested. For instance, if we are interested in the probability that x plus 1 plus x plus y plus z is smaller or equal than 1, then okay, so we can compute this by the formula. We have to integrate over E, okay, where E is the solid which is bounded by the 3 coordinate planes and by the plane x plus y plus z is equal to 1. And then f of x, y, z, dv. So E is the solid in the first octant bounded by x plus y plus z is equal to 1. Okay, and from this property you see how to compute this. So this integral will be equal to 1 over 8, and then if you project the solid onto the xy plane, what you have is x plus y is equal to 1. So the projection onto the xy plane gives you this line here, and you have to integrate first over this line. So x from, so this is 1 here, this is 1, x from 0 to 1, the y from 0 to 1 minus x, and the z from 0 to 1 minus x minus y, and then x times y times z, d z dy dx. Okay, and this is easy computation. Okay, so this shows you some applications in probability theory. You will learn much more in probability theory. Okay, so but the important thing is there are many applications of the triple integral, and also we didn't start from a problem like computing some volume as we have done for the double integral in order to figure out the triple integral. When we introduced the triple integral, the only thing we just looked at the definition for the double integral and extended it to dimension 3. But the triple integral is not an object which is useless, as you see here from those applications. Okay, so what is left is we have already seen for double integrals if we change to polar coordinates, then we have already figured out how such a change of variable affects the double integral. Now, what we want to do next is we want to figure out if we have given a triple integral and we want to change to either cylindrical or spherical coordinates, how does this affect the triple integral? Okay, so what is the effect of such a change of variable onto the triple integral? And this is like we will do this in section 15, or in the textbook it's done in section 15.8, and then in section 15.9 actually a general substitution theorem for double integrals and triple integrals is discussed. So actually the section 15.8 just discusses a special case of section 15.9, but important special case. So we still first look at it separately, and then in section 15.9 we are going to discuss the effect of a general change of variable onto double integrals and triple integrals. Cylindrical coordinates are easy. And we actually don't have to do much, because if we have given a function or triple integral, and E can be described, so E is a space region of type 1, so E can be described as so xy in some plane region, and this set larger or equal than u1 xy and smaller equal than u2 xy. Okay, so then we can write the triple integral as a double integral over d, and then the last integration goes from u1 xy to u2 xy, f of xy z dz dA. Now we assume that this space region can be easily described in cylindrical coordinates, which just means that okay, so you have this kind of form, and D can be easily described in polar coordinates. Okay, if this is the case, then you can introduce here cylindrical coordinates, because cylindrical coordinates are just in the xy plane. You choose polar coordinates, and you keep the z coordinate. Okay, if you do this, then so for instance, if D can be described in cylindrical coordinates, in polar coordinates, so by some r theta, where r is between A and B, and theta is between alpha and beta. Okay, so then we can use this in order to do the change of variable, but for this double integral here. So we get that the first integral, for instance, over r goes from A to B, the second integral over theta from alpha to beta, and then we have the integral from u1 xy to u2 xy, f of x, y, z. Sorry, x and y we have to replace x by r times cosine of theta, y by r times sine of theta, z. And we have an r from the change of variable to polar coordinates, and then dz, d theta, dr. Okay, and this, if you forget about this middle step here, okay, then this shows you how to change from if you have a triple integral and you introduce cylindrical coordinates, okay, this is what is going to happen with the triple integral, okay. So you have to integrate over the new region, okay, described in cylindrical coordinates, and you have to replace x by r times cosine of theta, y by r times sine of theta, and the effect on the dv is the additional r which comes from the introducing the polar coordinates. Okay, so this gives you another example for a change for a substitution in a triple integral. Okay, so but actually this is not very complicated, because we do not have to do here something new, because cylindrical coordinates are as I said, you just keep the z coordinate and you introduce polar coordinates onto the projection of the solid onto the xy plane. Okay, so that's why I will also skip here doing examples for cylindrical coordinates and instead go directly to spherical coordinates. Because for spherical coordinates we really have to prove something. So maybe just to remind you, spherical coordinates. We have given a point in the space, and we describe it as follows. So one coordinate is this angle, which we call phi. Okay, and the other coordinate is the length here of this line, which is called rho. Okay, and then you project this. The third one is you project this point down onto the xy plane, and you choose this angle here, theta. Okay, so we are going to describe this point here in cylindrical coordinates by this triple here. So rho, theta, and psi. Okay, and you see that if you have given a point in spherical coordinates, you can compute the Cartesian coordinates easily. So what you have to do is you have to look at this quantity r times sine of theta. This is this length here. So this is this length here, and then times cosine of theta. Y is equal to r times sine of psi, and then sine of theta, and z is equal to r times cosine of psi. So if you have given a point in spherical coordinates, that's how you can figure out the Cartesian coordinates. So what we want to do, now is okay, we have given a triple integral. And we wanna do this change of variable. Okay, so we wanna go from x, y, z to the new variables rho, theta, and psi. Okay, now if you remember the substitution rule for functions of for the normal integral, so if you have something like f of x dx, and here you go from a to b, and you do a substitution, you introduce a new function t. Okay, what you have to do is, okay, you have to figure out, okay, the new limits. So you have to go here from some alpha to beta, okay, where now in t phi of alpha is equal to a, phi of beta is equal to b. Okay, and then you have here, but the dx becomes the derivative of phi with respect to t dt. Okay, so if we have this, the triple integral, we introduce spherical coordinates. First, we have to figure out, okay, how does E changes. Okay, so this means you have to describe the solid E in spherical coordinates. Okay, and then you just plug in x, y, and z what you have here. But the main thing will be to figure out, okay, what happens with the dv. Okay, so this is the same as here you have to figure out what happens with the dx. So we assume that E can be easily described in spherical coordinates. If this is not the case, there is, it doesn't make sense to go to spherical coordinates, because the solid over which you integrate will become much more complicated. Okay, so we assume that there is an easy description of E in spherical coordinates. Okay, and we first look at the situation where E is in spherical coordinates. Okay, where the rho is between some a and b. What is the notation I use here? Just that I stick to the same notation. The theta is alpha between alpha and beta, and the psi is between c and d. Okay, so this is the description of E in spherical coordinates. I should maybe add this. Okay, so this is called a spherical wedge, and this can of course be easily plotted, but I have a slide where such a spherical edge is plotted, and it's the best thing to look at the slide, because then things become much more clearer. Okay, so here you have an example for such a spherical wedge here. Okay, so in spherical coordinates, what you see here is just a box. Now, what we want to do is, okay, we want to compute the triple integral over such a spherical wedge. Okay, now the idea should be pretty clear. So the idea is always the same. We divide this interval into, let's say, L sub-intervals, this interval into M sub-intervals, this interval into N sub-intervals, which means we divide the spherical wedge into sub-wedges. Okay, so first we introduce these sub-wedges. Now, if we Now what we can do is, so originally we have to integrate over the whole spherical wedge. Now we just look at the contribution from such a sub-wedge. The first thing we have to figure out, so the integral will be equal to, so the contribution of this sub-wedge is we have to choose a sample point inside the sub-wedge, okay, and we have to evaluate f at the sample point times the volume of the sub-wedge, okay, and then we add over all those sub-wedges, and this will give us a triple Riemann sum, and as n, as the subdivision here in all three coordinates tends to infinity, okay, this should give you the triple integral. Actually, this is something you have to prove, okay, to be strictly speaking, you have to prove this, because this gives you another way. This object is already defined, okay, and this gives you another way to compute things, okay, and you have to prove that those two ways of looking at things will give you the same result. Okay, so we first divide the spherical wedge into sub-wedges. Here you see already a sub-wedge, because you see here indicated rho I, which is because for this sub-wedge, maybe I should write it. So you have from rho I minus 1 to rho I. This should be here. Not precisely. Where is the rho I? Not really. It goes from rho I to rho I minus 1. Rho I, or I write it like this just to make things consistent. So here you have, for this one you have alpha I minus, or theta j minus 1 to theta j. And for the last one you have psi k minus 1 to psi k. Now, the triple integral over our wedge f of x, y, z dv. Here actually this e and this e is different, okay? Because this e is in Cartesian coordinate and this e is in spherical coordinates. Okay, so maybe I should differ them. So maybe I should add here a prime. Okay, this should be equal to, okay, that you compute the limit, you go L, N, and M tends to infinity, where this here is the number of intervals you choose for subdividing. And then you have the sum L from I from 1 to L, the sum J from 1 to M, or N. Let's choose the same order as in the English alphabet, and k from 1 to n. Then what you have to do is, okay, f evaluated at some sample point. Okay, this but this sample point is in spherical coordinates. Okay, so you have this. I need now space because this will. So I write this here because this will. So you have the in x, y, and z. So for x, I just showed you the formula. So you have rho I, some sample point. Okay, and then you have the sine of psi k, some sample point, cosine of theta j is also sample point. The same for the other rho I tilde, sine psi k tilde, and sine of theta j tilde. And the last one is rho I tilde, and then you have cosine of psi k tilde, some sample point, and multiplied with the volume of the of this wedge here. Okay, so multiplied with the volume of this subwedge here. This is what you actually see here. Okay. Now this volume, you see that if you make the subdivision very small, this wedge will look like a box. Okay. So we use the volume of a box in order to approximate it. Okay. You see that that this volume here is roughly, okay, roughly, because we approximate by a box. Okay, so you see that the height of the box is given by delta rho, okay, the subdivision of the interval for the radius. So the height is given by delta rho, okay. Then you see that this length here, this maybe I can show you this. Where's my cursor? I don't have. You see this, the length of this one here, okay, is given by, okay, the length of this one is rho I, and no, sorry, for this one, because the angle here which you see here is delta psi, okay, because of the subdivision. So this is this angle here, delta psi, and for this length here, okay, you have the length of this arc here is the radius times delta psi. Okay, and then what we need is the length of this here. For this we have to, because the delta theta, okay, is the projection, you have to project this down onto the xy plane. If you project this down, okay, what you get is for this length you get this one, and you have to multiply it with delta theta. Okay, so this will be this length here. Okay, so overall for this you have a delta rho. Okay, so this is once more. This is the length of this edge here. Then you have a rho I. Actually, it's rho I minus 1. Okay, because of the way I introduced the wedge. But let's stick to this picture. Rho I times delta psi, and from projecting down, you see you have this here. So another rho I, so rho I square sine of psi I, and then you have delta of theta. But this is roughly, okay. This is because here this is not really a box, okay. So this just gives you roughly the volume of the spherical edge. Now this is not very helpful, okay, because this just gives you roughly this here, okay. So you cannot see here the Riemann sum, okay, but it can be proved. That if you change a little bit rho I and psi I, okay, or more precisely, there exists a point, a symbol point in spherical coordinates, okay, such that for this here you get in fact equality. So Vij bar is exactly equal to some, if you change this a little bit, square, and you change this one should be k, you change this one a little bit, delta rho, delta theta, delta psi. And we choose here for the sample point the same point, okay, which makes here equality, just that everything fits together. And now we plug this in, and you see what you see here, triple Riemann sum. So this integral here becomes the integral over, so you go from alpha to beta, or you go from A to B, you go from alpha to beta, you go from C to D, then you have f of, and here you have to replace x, y, and z by this cylindrical, by these expressions here. And then this is the effect, okay, onto the dv. So you see you have a rho square, you have a sine of psi, and then you have then you have a d psi, you have a d, what's the second one is theta, and the d rho. So what you have to do if you change to spherical coordinates is you replace E by the solid in spherical coordinates. You replace x, y, and z, okay, by the relations, okay, with which you can change from spherical coordinates back to Cartesian coordinates. And the dv you have to replace by this here, rho square times sine of psi times this here. Okay, we will see in the next the next section, if you do a general change of variables, okay, where you choose any, so you replace x, y, z by 3 new variables, for instance, r, s, t, okay. We will discuss in the next section, okay, what is the impact of such a change of variable onto the dv in general. And this will then become a special case. But this is already the idea, the rough idea how to proceed in the general case. Okay, so maybe let's do some examples just to see how this is applied. For instance, compute the volume of the smaller wedge cut from a sphere of radius a by 2 planes that intersect along a diameter at angle pi over 6. Okay, so we have a sphere. We have 2 planes which, as intersection, have a diameter of the sphere. Okay, and those 2 planes, okay, will slice the sphere into 4 parts. Okay, into 4 wedges, and you should compute the volume of one of the smaller of the wedges. There are 2 of them. Now, the easiest way to solve this using spherical coordinates. So what you do is, because actually for this exercise you have free choice of how to place the sphere into your coordinate system. So you will place the spheres and the planes into the coordinate system in such a way that the description gets as easy as possible. Okay, so what you do is you place the sphere. You place the sphere into the origin of the coordinate system. Of course, you will do this. Now, how to choose the 2 planes? Okay. Now, one plane you can choose, for instance, the xz plane. Okay, so this will be one plane, and the other plane you choose a plane which is like this here. So the diameter where they intersect, okay, should be the z-axis. Okay, so you have 2 planes like this here. One is the xz plane, and the other one is like this. Okay, so this is the other plane, where you have here the angle. So this angle is pi over 6. So you have those 2 planes, okay, and the sphere. So this is the most easiest way to look at this example, okay, because then you see already you have to, this is now easily described in spherical coordinates. Okay, so the integral over E dv, because we have to compute the volume, is equal to, now you see that the theta is from 0 to pi over 6, the psi from 0 to pi, which is like this, 0 to pi, and the rho from 0 to 1, from 0 to a. So you have the integral. The order doesn't matter. So maybe first over theta, then over psi, and the last one over rho. Okay, so you go. I didn't draw here the sphere, okay, but the sphere, because the sphere is not so easy to draw. Okay, you just have those two planes here. So this, so once more, the theta goes from 0 to pi over 6. Okay, from here to here. The psi goes from 0 to pi, and the rho from 0 to a onto the sphere. Okay, but here I have already done the change of variable. Okay, so I have to write here now the rho square times sine of psi. Okay, which is the effect of the change of variable. So don't forget this. And then you have the rho, the what is the second one is psi, and the last one is the theta. Okay, you see that the function can be written as a product of a function of rho, a function of psi, and the function of theta. So the integral is just the product of the three integrals. So this integral is equal to the integral over rho is the most, the integral over theta is the most easiest one, okay, because there is no theta here, so pi over 6. Then you have still the integral over rho squared d rho, and the integral over psi. Okay, so this one is 2, and this one is so pi over 3, and this one is a to the cube over 3. So what you have is pi times a to the cube to the 9. Okay, so this is one example. Another one, for instance, this one. So if you have to compute this integral, the integral from minus infinity to infinity, the integral from minus infinity to infinity, the integral from minus infinity to infinity, square root of x squared plus y squared plus z squared e to the minus x squared plus y squared plus z squared. Now, what you want to do here is, because of the special form of the function dev, because of the special, sorry, dz dy dx, because of the special form of the function, okay, because if you introduce spherical coordinates, this function is getting much more easier, because this is just rho square and this is also rho square. So you suddenly want to change to spherical coordinates. Okay, if you do this, then because we have to integrate over the whole space. Okay, so the first one, let's say, with respect to rho. So rho from 0 to infinity. Then the theta from 0 to 2 pi, and the psi from 0 to pi. And then you have here rho e to the minus rho square. And what you should not forget is the rho square times sine of psi from the change of variable. Okay, and then you have d psi, d theta, d rho. Okay, and if you compute this, you will get 2 pi. I'm not going to do this. But you see, the rest is easy. So the only thing you have to remember is, if you do a change of variable, then you have to a change of variable. Okay, if you replace x, y, and z, if you change from Cartesian coordinates to spherical coordinates, you have to replace z by rho times cosine of psi, x by rho times sine of psi times cosine of theta, and this y by rho times sine of psi sine of theta. This is what happens with the integrand. Then you have to replace the region over which you integrate, the space region, by the corresponding space region described in spherical coordinates. And here, for this dz, dy, dx, okay, if you change to spherical coordinates, okay, you have this additional factor which you have to multiply. Okay, and you see also that introducing spherical coordinates will make sense whenever the solid over which you integrate is easily described in spherical coordinates, and the function involves something like x squared plus y squared plus z squared, or something which gets easy if you introduce spherical coordinates. Okay, even so, if the function is not getting too easy, okay, but if the domain is getting if the domain over which you integrate is getting much easier, then normally introducing spherical coordinates is helpful in order to compute triple integrals. And introducing cylindrical coordinates is helpful if also the space region over which you integrate is easily described in cylindrical coordinates, and the function just involves, for instance, the function is a function of one variable of the expression, for instance, x squared plus y squared, and normally you get something easy. Okay, so on Monday we are going to discuss a generalization of this here to a general change of variables. So on Monday we will discuss a general theorem which has this here as a special case, and this is also the last section which we have to discuss from the curriculum we have to cover this semester, and then we will go on to to chapter 16. Now, as for the final, in 2 weeks. Now, what is covered by the final? So chapter 14 completely, and chapter 15. Here section 15.1 up to what I taught today, 15.8. So everything except the final section from chapter 15. Okay, so this will be the material covered by the final exam. So it should be June 5th, right? Or is it June 5th? No. Yes. So June 6th. Should be June 5th. Right? Is it June 5th? No? 5th. Okay, so any questions? If not, then we will meet on Monday.